In this lecture, we will do the analysis of RLC series and parallel circuit. We will get the resonance condition. In that, we will derive the equation for resonant frequency and the quality factor that is known as voltage magnification of resonance circuit. The purpose of doing this analysis to use in various applications like oscillatory circuit, for radio receiver circuit, television circuits, for tuning to select new frequency, in filter circuit like low pass filter, high pass filter, band pass, band stop filter. So there are so many applications of RLC series and parallel circuit. So first we will see RLC series circuit. In RLC series circuit, R, L and C, three elements are connected in series combination, that is connected across AC supply voltage V equal to Vm sin omega t. So in circuit, I is total current of the circuit, VR voltage drop across resistor, it is given as I into R, VL voltage drop across inductor, that is given I into XL. XL known as inductive reactance, it is known as opposition offered by inductance to flow of current. Vc potential difference across capacitance is given by I into Xc, Xc known as capacitive reactance, opposition offered by capacitance to flow of current. The unit of XL and Xc are ohm. In RLC series circuit, we have different parameters: total current, VR, VL, VC and supply voltage V. So here we have to do the vector summation. For that, we need to plot the phasor diagram. So in phasor diagram, circuit current remains same, so we have to take as a reference quantity VR that remain in phase with current. So VR in phase with current, VL leads the current at 90 degree and VC lags the current by an angle 90 degree. So by doing this analysis, we are getting three conditions. First condition is VL greater than VC. So here inductive voltage is greater than capacitive voltage. So this condition is known as inductive, and circuit behaves as inductive circuit. So in inductive circuit, current lags the voltage, so power factor is always lagging. Second condition is Vc greater than VL. So here capacitive voltage is greater than inductive voltage, so circuit behaves as a capacitive circuit. So in this, current leads the voltage, so power factor is always leading. Third condition is VL is equal to Vc, so inductive voltage becomes equal to capacitive voltage. So circuit behaves as a resistive circuit, and resonance condition takes place when VL becomes equal to Vc. So one by one we will see all three conditions. So first we will see VL greater than Vc. So in this condition, we are considering VL greater than Vc. So in phasor diagram, we have to take VL minus Vc. So this side is VL minus Vc. So this one is also equal to VL minus Vc. So here we have taken current I as a reference, VR that remain in phase with current. So the phasor sum of VR and VL minus Vc, that is given by V, and this is a phase angle. This is the phase angle phi. So from the phasor diagram, we can obtain V. So V is given by under root VR square plus VL minus Vc whole square. So by substituting the parameters, we will get V is equal to I under root R square plus XL minus XC square. So we will get the current equation I is equal to V upon under root R square plus XL minus XC whole square, where this denominator term is called impedance of the RLC series circuit, and it is defined as opposition offered to the flow of current. So in AC circuit analysis, the current equation that becomes V by Z, so voltage equation is V equal to I into Z. So Z is combination of RLC load. Cos phi, that is known as power factor of the circuit, so that can be obtained from the phasor diagram. So that is equal to VR by V. So by substituting, we will get R by Z. It is ratio of resistance to impedance. Second condition is Vc greater than Vl. So in phasor diagram, we have to take Vc minus Vl. So by having the equal side, Vc minus Vl, so this one is also Vc minus Vl. So this is phasor sum of V and this is phasor sum of V, that is between Vr and Vc minus Vl. So to find the magnitude of V from the phasor diagram, V is equal to I under root r square plus xc minus xl square, that we already derived in first condition, VL greater than Vc. So the current equation becomes I equal to V by Z, where Z is impedance of the circuit. Power factor remains same in both the condition. Cos phi is equal to R by Z. Now, while analysis of RLC series circuit, resonance condition takes place. So here in resonance condition, we will find the resonant frequency. So in the circuit diagram, according to the KVL, V is equal to VR plus VL plus VC, summation of all voltages. So we can write this voltage in rectangular form in terms of showing the real and imaginary part. So it is given as I into R plus J I into XL minus J I into XC. So in the equation, impedance Z is equal to R plus JXL minus JXC. So this is the rectangular form. So from that we can derive the magnitude of Z. So it is given as Z is equal to under root R square plus XL minus XC whole square, as XL equal to omega into L and XC is equal to 1 upon omega C. But we know omega equal to 2 pi f. So by substituting the omega, we will get under root R square plus 2 in bracket 2 pi FL minus 1 upon 2 pi f into C whole square. So in the circuit diagram, we have taken variable frequency supply source, and we know the relation between frequency, inductive reactance and capacitive reactance. XL is equal to 2 pi f into L and XC is equal to 1 upon 2 pi f into C. So by varying the frequency, means by increasing the frequency, XL increases where XC decreases. So by changing the frequency at one point of frequency, we will get XC is equal to XL. So at one frequency, the value of inductive reactance becomes equal to capacitive reactance, is called the resonant frequency. Now we will derive the resonant frequency equation. So during resonance, X becomes equal to 0. So X is called net reactance of the circuit. So X is equal to XL minus X is equal to 0. So by transferring the term, it becomes XL equal to XC. So XL is equal to omega L and X is equal to 1 upon omega C, but here resonance takes place. So here in subscript, we are denoting small r. Okay, so that shows the resonance condition. So by mathematical explanation, by the formulation, we will get the Fr is equal to 1 upon 2 pi under root LC. During resonance condition, net reactance becomes equal to 0, X is equal to XL minus XC, that becomes equal to 0. So impedance becomes Z equal to under root R square plus X square, where X is equal to 0. So impedance becomes equal to R. So this is the minimum value of impedance. So during resonance condition, impedance becomes minimum, whereas current becomes maximum according to the equation I is equal to V by Z. So I max is equal to V by Z is equal to V by R. Here a resonance curve is given, that is frequency versus current. So with very small value of R, the current frequency curve is becomes sharply peak, but for the larger value of R, it becomes very flat, or it becomes minimum. So that shows the relation between frequency and current, and in accordance with the resistance value. Now Q factor for the RLC series circuit, that is known as quality factor. Quality factor is also known as voltage magnification produced in the resonance condition. So Q factor is also called is equal to Q factor is equal to voltage magnification. As we know, during resonance current becomes maximum, so it is taken as Im is equal to V by R, so V is equal to Im into R. Voltage across inductor or capacitor is given by Vc is equal to Im into XL, or VL is equal to Im into Xe. So voltage magnification is defined as ratio of voltage across L or C to the applied voltage. So by substituting VL by V or Vc by V, by further simplification, we will get Q factor is equal to 1 upon R under root L by C. So Q factor, that is known as quality factor of the RLC series circuit, that also decides the quality of inductive coil. Bandwidth of resonant circuit. So bandwidth is defined as the band of frequencies. So in the diagram, the band of frequencies given on either sides. This is band of frequencies which lies between 2 points on the either side of resonant frequency. So in the diagram, Fr is resonant frequency on either side. So F1 and F2. So it is denoted point A and B. So the band of frequency which lies between on either side of resonant frequency, where current falls to 1 upon root 2 of its maximum value. So at Fr we have maximum value of current, but at point A and B it falls to 1 upon root 2 of its maximum value. So bandwidth is defined as delta F is equal to F2 minus F1, or it is also given as delta omega is equal to omega 2 minus omega 1. The unit of bandwidth is Hertz. It is also defined as ratio of resonant frequency to the Q factor. Now we will see the examples of RLC series circuit. So in the example, a circuit has resistor R equal to 10 ohm, inductor L equal to 10 millihenry, and C equal to 1 microfarad. The applied voltage is given 230 volt at resonant frequency. So here in calculation, we have to calculate resonant frequency, current in the circuit, voltage across each element, that means VR, VL and VC. And in further, we have to also find Q factor and bandwidth. So in given data, R given 10 ohm, L 10 millihenry, so it can be write 10 into 10 raised to minus 3 Henry. So 10 raised to minus 2 Henry. C is equal to 1 microfarad, so in farad 1 into 10 raised to minus 6 farad. So resonance frequency, we know Fr is equal to 1 upon 2 pi root LC. So by substituting the values, we'll get resonance frequency is equal to 1591.55 Hertz. Now we know the current becomes maximum during resonance, so Imax is equal to V by R. So by putting the values, we'll get 23 ampere. XL inductive reactance is equal to 2 pi Fr into L due to resonance. So we'll get XL equal to 100 ohm. Xc capacitive reactance, it is given by 1 upon omega C is equal to 1 upon 2 pi FRC. So X is equal to 100 ohm. So as we know, during resonance, XL becomes equal to Xc, so we are getting same value of 100 ohm. Now here we need to find voltage across each element, VR, VL and VC. So we know the relation VR equal to I into R, so we'll get 230 volt. VL is equal to I into XL, so we'll get 2300 volt, and VC is equal to I into Xe, so we'll get 2300 volt. Q factor is equal to 2 pi FRL divided by R, or we can also express is equal to 1 upon R under root L by C. So we'll get the same value by using any expression of Q factor, so it is 10. Bandwidth, it is ratio of resonant frequency to the Q factor, so we'll get 159.155 Hertz. Now we will do the analysis of resonance in parallel RLC circuit. The same concept or the same funda that we will get in parallel RLC circuit. So in resonance of RLC series circuit, the power factor becomes unity of entire circuit. So same here we'll get the entire circuit becomes unity in parallel RLC circuit. So in the circuit diagram, usually the R, L and C, all three components should be in parallel, that is connected across supply voltage. But in the circuit diagram, we have considered inductance has small value of ohmic resistance, so that should be connected in series combination. So here R and L branch connected in series. So that is connected in parallel with capacitor. Here we use pure capacitor. So R, L series combination, C in parallel with RL combination, that is connected across variable frequency supply source. So here we will get the resonance condition by doing the analysis of this parallel RLC circuit. Before that, we have to do the vector summation or phasor summation, so we need to plot the phasor diagram. So in phasor diagram, we have parallel circuit, so voltage remains same, so we are taking as a reference quantity total current that remain in phase with voltage, so that consider in phase with voltage. Now here we are considering the inductive circuit, so the IL component that resolve into two component, IL sin phi L and IL cos phi L. Here IC that leads the voltage, so it is considered in terms of leading. So by consideration of inductive circuit, it is resolved into two components. So by doing the phasor summation, this is IR is equal to resultant current. So when the resonance condition takes place in parallel circuit, the necessary condition is IC equal to IL sin phi L. So we have to get the capacitive current, inductive current and this sin phi L. So we'll get the resonance frequency for the parallel RLC circuit. So current in capacitive branch IC is equal to V by XC. Current in inductive branch IL equal to V by ZL. We consider here ZL because we have R and L in series combination. So for the combination of load, we have to consider the impedance, where ZL is equal to impedance of the inductive branch. It is given in rectangular form and magnitude form. Phase angle phi L is given by tan inverse XL by R from the phasor diagram, and sin phi L is equal to XL by ZL from the phasor diagram. IL sin phi L is equal to, by substituting IL and sin phi L, we will get V into XL upon ZL square. So by substituting equation 2 and 7 in equation 1, we will get V by XC is equal to V into XL upon ZL square. So ZL square equal to XL into XC. So by substituting the value, we will get FR is equal to 1 upon 2 pi under root 1 upon LC minus R square by L square. But as I earlier told, we have taken small value of ohmic resistance. So by ignoring this, by putting 0, we will get FR is equal to 1 upon 2 pi under root 1 upon LC. So that is same as for the series circuit. Q factor for the parallel RLC circuit, so it is called current magnification that occurs in resonance parallel circuit. So Q factor is equal to capacitive current or inductive current to the resultant current. So we know IC is equal to IL sin phi L and I is equal to IL cos phi L. So it's equal to tan phi L. So tan phi L is equal to XL upon R is equal to 2 pi FR L upon R. So from the phasor diagram, here we have to find the resultant current. So resultant current I is equal to, from the phasor diagram, I is equal to IL cos phi L. So it can be written as I is equal to IL cos phi L is equal to IL is equal to V by ZL, cos phi equal to R by ZL. So it is equal to VR ZL square. But under the condition of resonance, we already derived this ZL square. So that is given here. So we can directly substitute in the equation. So it is equal to L by C. So the resultant current is given by VR upon L by C. So by shifting the R into denominator, so we'll get resultant current is equal to V upon L by CR. So L by CR, that impedance offered by the parallel circuit. So during parallel resonance, the impedance becomes maximum whereas current becomes minimum, and power factor remains unity.